Thank you for the introduction. So the last talk before lunch is about callbacks, and this is joint work with Romain Tomasetti. So this is a talk about callbacks, and to introduce a little bit which callbacks we are talking about, I have this snippet here from Kokkos. So many functions in Kokkos are instrumented for callbacks. And the snippet here comes from the file Kokkos parallel in Kokkos. And what we're looking at is the implementation of parallel 4. And here at the center, we see really the heart of the implementation. And this is where Kokkos creates the closure and then calls execute on the closure. But actually, right before that, Kokkos checks whether the user has set a function as a callback it should call when it begins a parallel 4. And if so, it calls this function that the user has set and provided some contextual information. And right after, it does the same, but now for an end parallel 4 callback. So these are the kinds of callbacks that we'll be talking about in this presentation. And I will be describing some utilities that we made to ease the use of these kinds of callbacks. So the presentation, I will start with describing the current state of the callbacks in Kokkos, then describe some of these new utilities that we made, and then 2 use cases. Okay, so the callbacks in Kokkos have a C-style API. And when you want to set a callback, you basically have to provide a function pointer. So if you want to set a begin parallel 4 callback, you have to provide a pointer to a function that takes these arguments, which are essentially the arguments that Kokkos wants to pass to a callback of this type. And the function should return void. Most users don't set callbacks explicitly, but when they are confronted to callbacks, that's usually through the use of Kokkos tools. So the Kokkos tools repository has all kinds of tools, like a kernel logger, a kernel timer, and so on. And they work by setting callback functions in Kokkos. And the same is true for vendor profiling tools, which can also collect contextual information through setting Kokkos callback functions. If you do want a more hands-on approach and define your own callback function and set it within Kokkos, then Kokkos has for each type of callback a setter. And this snippet here is an example from client code, so from this case from ArborX. And here, ArborX is using the set begin parallel 4 callback setter from Kokkos to set a specific client code specific callback. In this case, that's provided in the form of a lambda. The capture list is empty. And so we are essentially providing here a function that can take these arguments, which Kokkos wants to pass to this kind of callback. And then this is what, in this case, ArborX wants the callback function to do with those arguments. So you can see that the the capture list is empty. And that's important because it's actually non-capturing lambdas that C++ can convert to function pointers. I've showed you only one signature for a callback. It's actually more generally true that the callbacks in Kokkos don't have a void star user data pointer. And that kind of argument can be important to allow stateful lambdas to be provided as function pointers. So Kokkos doesn't have that. And so in principle, the callback functions that you can set are stateless. So if you want to do something with a state, you have to use, as it currently stands, sort of a global state mechanism. Okay, one really important use of callbacks now internally in Kokkos is in the Kokkos tests. That's actually used in Kokkos tests to validate API calls. So there are many important use cases. So if you write your piece of code in Kokkos, it can be important to check the lifetime of objects. So do allocate data, deallocate data, does that happen at the right moments? Are these API calls made at the right moments, and so on? If you do things with parallel 4 synchronizations, is that orchestrated right? So it's important to be able to check API calls. And facilities for that are provided in the file tool testing utilities, which is in the unit test folder in Kokkos. And the way it works is that this file starts from the principle that most of the API calls in Kokkos are associated with callback calls. So an API call in Kokkos will typically trigger some callback calls. And so you can listen to the callback calls to make sure that the API calls happened actually as you expected. So the machinery that this file puts in place is to associate each type of callback with an event. And an event is a struct. So the begin parallel for callback is associated with a struct begin parallel for event. And so the type of this struct characterizes the type of the callback. And this struct will have a number of arguments, and those arguments are the arguments that Kokkos typically passes to a callback of this type. And then in this file, the tool testing utilities, there is also this machinery to run a piece of code, listen to the callbacks, push those callbacks as events into a container, and then check at the end whether that container of events contains the events that you expect there to be based on the API calls that you expect to be made. Some observations. So this is part of Kokkos tests. It's an important capability. It could be useful for users, but because it is in Kokkos tests, it is not installed with Kokkos. So users cannot currently use this in user code. The design of the events is a bit complex, so I describe it like aggregates, but the design actually is more complex, and if you're able to read code quickly, you will see that it is actually using the CRTP. And then this capability in this file to check containers of events seems to have some overlap with Google Mock container matchers. Okay, so we'll now switch to describing a bit the utilities that we made. So we wanted to use these things. The events seem very important to us, but they are not installed with Kokkos. So we basically had two options, patch Kokkos to install this file, or make our own version. And because we saw some opportunities to do things a bit differently, we chose the second route and made a new version. And so in our version, we likewise associate callback calls with events, but our events are just simple aggregates. So for the begin parallel for call, we have a begin parallel for event with just these members. The tool testing utilities file has much machinery to sort of group events of similar types. It defines, for example, the profile section manipulation events, which are related with create profile section, destroy profile section, start profile section, stop profile section. The common trait that they have is that they all have a member variable section ID, and in tool testing utilities, as it stands, that group is created through an inheritance principle, but you can actually use new language features like concepts to also define that trait. So this events, like in tool testing utilities, it allows filtering of events based on types and attributes. That's similar to tool testing utilities. One thing that we try that is a bit more novel is that these events associate actually types with callbacks of different nature. And so it opens a bit the door to using callbacks more with C++ template metaprogramming, because you now have types. So that's shown a bit here. As it currently stands, if the user wants to set a callback, it has to provide a C-style function pointer. With our utilities, what we allow the user to do is to set a callback as a C++ function object that has a call operator that can be invoked with an event of a certain type. So if the user wants to set a begin parallel for callback, the user can provide a function object with a call operator that accepts a begin parallel for event. And sort of to bridge the C-style interface of Kokkos and these C++ style listeners, we have a manager class. So the way it works is that the user can register with our manager a listener, and then the listener will, with type trace, detect which call operators for which event types the listener has, set the corresponding callback functions, Kokkos, and then when the program runs, the manager intercepts the callback calls and sends them as events to the registered listeners. And our manager is interoperable with any Kokkos tool loaded dynamically. I don't know how much time I have left. I'm sorry? Just a few more minutes. Okay, so two use cases. The first use case is about benchmarking and timing kernels in pieces of user code. And so what we have in mind is sort of a region of code where you have multiple parallel regions. And you may want to know, well, what is the time that running this parallel region takes? Because maybe you have different possibilities for implementing it differently. You want to know which one is fastest. Or in your CI/CD, you want to run always this code and want to track how long this region takes to make sure that you don't have regressions. Timing, there is many approaches. You can put in timers, you can put in fences to make sure that you time whatever you intend to time. But those approaches typically are intrusive. You have to make changes in your code. And what we propose here to do with these callbacks is have a non-intrusive approach to timing, where you actually can keep your code as it is, and you don't have to modify the code with injecting timer code or fences. So we want to use the callbacks to make a non-intrusive approach to timing. In one or two slides, I will show you an application. It comes from Helm, which is the finite-element code that we developed in our group. Finite elements built on Trinos, Kokkos kernels. Current applications are sort of electromagnetism simulations for semiconductors. And the application comes from where in the code we are constructing the sparsity structure for the finite elements. So timing, it's complex because Kokkos is doing the dispatch on host, but that's actually just enqueuing the work. The work is then done on device in a stream. And so if you just use host timers, you would basically just time the dispatch, and you wouldn't necessarily time the workload itself on device. So as I said, you can do synchronization, host timers, and so on. You can make it work, but we want to be non-intrusive. And so we remember that before it does the dispatch, Kokkos makes a begin parallel for callback, and after it does the dispatch, it does a end parallel for callback. So what we did is that we make a listener, we call it timer listener, which listens to begin parallel for callbacks and end parallel for callbacks. And when it hears a begin parallel for callback that matches the region that we are interested in, it records a marker into the stream. And when it hears a end parallel for back that matches the region that we're following, it inserts a end marker into the stream. And these markers that I talk about are the CUDA event record markers, so defined in the CUDA event management API, and there is also on HIP the HIP event management API. And these markers are such that they track the time at which they are processed on device. And so when all the work is done, you can query these markers and ask what is the time elapsed between the two of you, and that gives you a proxy for the time that the workload took. So to put it together, this is an example of how it works with Google Benchmark. So in the benchmark, we have sort of it's a benchmark fixture, so it has a setup, and in the setup, we create the timer listener, and we tell it, well, you have to listen to begin parallel 4 and parallel 4 that have a label that matches this name. And then in the run part of the benchmark is going to run the code. And actually then the listener is going to listen to the callback calls when it hears the begin end that we want to track, it inserts the markers into the stream. And when the work is done, we query the listener that queries the markers to know the time, and we pass it to the benchmark engine. This here is a result that we obtained that helped us decide on how to implement the graph. So just the last few minutes for another application. So I've talked a bit about the importance of being able to validate API calls. This is another illustration of how that can be important. So our code helm is built on top of Trinos. Trinos is built on top of Kokkos kernels and Kokkos. And then depending on the backend, you have the vendor stack all at the bottom. And so the user, or we as users, develop our code at the top. And so we use high-level API. And when we compile the code and we run the code at runtime, we hope that the high-level API calls get mapped through the stack to optimize low-level API calls. And that can be very complex. And you may want to verify that the high-level API calls are actually mapped correctly to the low-level API calls. In a Trinos stack, that mapping, if you think about linear algebra operations, happens in Kokkos kernels. And when Kokkos kernels does such a mapping from a high-level API to a low-level API, it actually pings a Kokkos callback. And it says, well, hey, I push this region, and in this region, I am doing this mapping of the high-level API to a low-level Q+ call. So one way to verify that you have set up everything correctly and that the high-level APIs are mapped correctly to low-level APIs is to execute a piece of code, record the callbacks that Kokkos made during that time, push all that in a container, then afterwards verify that that container indeed contains, in this case, a push region event with the name that includes that Q+ marker. Here I wrote the assertion with a Google mock container matcher, and the result is actually quite nice and quite descriptive of what you intend to verify. Okay, so these are some takeaways. So we described some utilities that we designed to manage Kokkos callbacks, opportunities to contribute to Kokkos. It seems being able to work with these callbacks and these test utilities are very important, not only for Kokkos, but also for user code. And so it may be interesting to promote this and make this available in core so that it's installed with Kokkos. In our own version, we found that it is possible to simplify a little bit the design of the events. Maybe interesting to have Google mock as a dependency and use the Google mock container matchers. Maybe there's an interest in contributing this callback manager to Kokkos or Kokkos tools. If you're interested in this work, we have our repository for our group. So our group is at the University of Liège. Our group is called CSM, so Computational Stochastic Modeling. So this is the GitHub name, Liège CSM. And then the repository is called Kokkos Utils, where we have this work on callbacks here. And then also some other things like some exploratory work on concepts, some view utils and other things. The first day we heard that Kokkos is now trademarked, so we will probably have to change the name of the repository, but for now you can find the tools here. We'll be happy to interact with you. Thank you very much for your attention.
We have time for one quick question because I think everyone wants to go for a lunch, and I think you're available and people can talk during lunch with you. So, yeah, maybe we move the question session to lunch. So, okay.
Thank you.
Let's thank all the speakers again.